So this is your incident particle. Okay, so this incident particle or target particle is bombarded by incident particle. So after this reaction, there are two daughter nuclei are created, that is C plus D. So C and D are daughter nuclei. Okay, daughter nuclei. And let us assume the rest mass of A is Ma, the rest mass of target is Mb, rest mass of C nuclei or daughter nuclei is Mc, and rest mass of D daughter nuclei is Md. And further assume that kinetic energy of A incident particle is Ea. So Ea means kinetic energy of a particle or incident particle. The kinetic energy of target nuclei is, let us assume this is your Eb, and for C daughter nuclei it is Ec, and for D it is Ed. So nuclear the energy is conserved in nuclear reaction, right? So what you can write from here, from energy conservation of energy. Oh. So what you can write, that total energy of a nuclei is its rest mass energy plus kinetic energy, right? So rest mass, since rest mass is A, so rest mass energy will be Ma c square. Kinetic energy is A. So this is your the total energy of incident particle A. Then total energy of target will be simply Mb c square plus kinetic energy Ev, and that should be equals to the total energy of daughter nuclei. So obviously it will be Mc c square plus Ec. Then you will have Md c square plus Cd. So I'll bring rest mass term on the left hand side and kinetic term on the right hand side. So if you rearrange it, so it will be Ma plus Mb minus Mc minus Md. So C square will be common from all mass term. Then you will have Ec plus Ed minus Ea minus of Ev. Okay. So this is the sum of the mass of the reactant, right? This is the sum of the mass of, if you take minus common, so it will be Mc plus Md, right? From these two terms, if you take minus one common. So this will be the sum of the mass of the daughter nuclei. This is the sum of the mass of the kinetic energy of product minus sum of the kinetic energy of reactant, right? So this is basically defined as Q value. Okay. So Q value is nothing but difference in the mass, or you can write in terms of difference in the kinetic energy. So if you write in terms of mass, so mass, sum of the mass of reactant minus sum of the mass of product into C square. Okay. Or in terms of kinetic energy, it will be sum of the kinetic energy of the product minus sum of the kinetic energy of reactant. Now Q can have three cases, like Q can be greater than 0. Okay. Or it can be less than 0, or it may be 0. Okay. So if Q greater than 0, then what you can say from this mass term, so it means this difference should be greater than 0, right? So Ma plus Mb minus Mc minus Md, that should be greater than 0. So what you can write from this equation, that Ma plus Mb should be greater than mc plus md, right? So after reaction, if see the mass of the sum of the mass of the reactant is greater than mass of the product. So in this reaction, there is a loss of energy, loss of the mass after reaction, right? Because reactant has higher mass as compared to the product. So what you can say, in this reaction, there is a loss of energy, and that of loss of energy is converted to converted to kinetic energy of the product. So in this reaction, Q is greater than 0 means there is a release of energy. Okay, there is a release of energy, and that release of energy is in the form of kinetic energy of product or daughter nuclei. Okay, so whatever energy will be released, that will be in the form of kinetic energy of C and D. And also this Q is greater than 0 is known as exothermic reaction. So here the loss of mass is converting to energy or kinetic energy, right? From Einstein theory, E equals to mc square also you can say. Since there is a loss of mass in this reaction, so that mass is basically converted to kinetic energy of daughter nuclei. So this is known as exothermic reaction. Okay.
सर
हाँ
एक बेसिक डाउट है, पूछूं क्या?
हाँ जरूर.
सर यहाँ डॉटर आपने जो बोला ना, मतलब जितनी ज्यादा एनर्जी होगी वो एग्जिट होती है कि वो काइनेटिक एनर्जी ऐसा यूज होती है, कि दोनों प्रोसेसेस होते हैं?
देखो यहाँ पे कुछ आपका एनर्जी रिलीज होगा. हाँ, मैं इस प्रोसेस की बात
यस.
कर रहा हूँ. सो दैट एनर्जी विल बी इन द फॉर्म ऑफ काइनेटिक एनर्जी. ये जब प्रोड्यूस होगा तो फिर क्या होगा, इसका एक रेस्ट मास एनर्जी होगा और एक काइनेटिक एनर्जी भी होगा. ये काइनेटिक एनर्जी कहाँ से आ रहा है? ये आपका जो एनर्जी रिलीज हो रहा है ना, यहाँ से कंट्रीब्यूट हो रहा है वो. इज इट क्लियर नाउ?
ओके.
हाँ, और यू कैन से इन अदर वर्ड्स that kinetic energy of the product will be higher than the kinetic energy of reactant. So whatever energy will be released during that alpha decay discussion also I told you that whatever Q will be released, that will be in the form of kinetic energy. Okay, that will be in the form of kinetic energy, but for alpha particle maximum energy was shared by alpha particle since it is very light particle. Okay, as compared to daughter. Now there are another case. So there are
Sir,
another
energy is released from daughter nuclei.
in this sorry.
Energy is released from C and D.
Yeah, in this process, there will be production of C and D, and there will be release of energy also. That energy actually basically in the form of kinetic energy of C and D.
Okay.
So, okay, so there will be release of energy. That energy in the form of kinetic energy of these two fellow.
Okay.
Okay, very simple word. Okay. Now, second case is Q less than 0. Shall I erase? Shall I erase?
Yes, sir.
Hmm.
Yes, sir.
So another case is when Q less than 0. Okay, this is known as endothermic reaction. So in this process, you can clearly see if you substitute that Q less than 0, it means Ma plus Mb should be smaller than Mc plus Md, right? So there is an increase of mass, right? Mass is increased. Okay, so after reaction, mass is increased, right? So product mass is higher than that reactant mass. So mass is energy, so you have to supply some energy from external. Okay, no? So here after reaction, mass is of the product is higher than the mass of reactant. So that increased mass, for this increment of mass, you have to supply some energy. Okay, so that energy will be converted to mass from Einstein energy mass relation. So that energy, that external energy will be what? So your delta E energy you are giving from external source. So external source will be what? External source will be that kinetic energy of that incident particles. So you have to give at least delta E amount of energy so that this reaction can take place. Is it clear that what I'm saying? So
Yes, sir.
since after reaction mass of that product is increased, so you have to supply some energy from that external source. Okay, so you have to supply delta E amount of energy. That energy will be corresponds to what? MC plus MD minus MM plus MB. Okay, that energy, that external source is what? The kinetic energy of a particle or incident particle. So you have to supply delta E amount of energy, minimum energy, so that this reaction can take place. Okay.
Sir,
Yes.
सर इस Q इज स्मॉलर देन 0 में जो
हाँ
रिएक्शन था हम उसमें लेफ्ट साइड में Q ऐड करेंगे यानी कि
नहीं, ये तो देखो Q लेस देन 0 आपका रिएक्शन क्या था? यही था ना, Ma प्लस MB माइनस MC माइनस MD, यही तो था. अब Q लेस देन 0 करो आप, तो इसमें से क्या लिख सकते हो आप? Ma प्लस MB.
नहीं सर वो समझ आया.
हाँ
मैं बस ये पूछ रहा था कि जैसे कि हम जो रिएक्शन लिखते हैं उसमें हम प्लस Q करते हैं रिएक्टेंट
हाँ हाँ
उसमें प्रोडक्ट
यस,
में, तो
हाँ
इसमें
यहाँ
हम
पे करना पड़ेगा,
रिएक्टेंट में प्लस Q करेंगे.
यहाँ पे करना पड़ेगा. यस, मतलब यहाँ पे आप एनर्जी दे रहे हो है ना, तो यहाँ पे करना पड़ेगा. ठीक है.
सर इसका मतलब ऐसा ही है ना कि ये रिएक्शन अगर हमें करना होगा तो हमें कुछ तो एनर्जी सप्लाई करना पड़ेगा.
Exactly, exactly. Okay, so you have to give some energy. Okay, is it clear now?
Yes, sir.
सबको समझ में आया ये?
Yes, sir.
ठीक है. So this is known as endothermic reaction. Next is when Q is 0. So Q is 0 means what? The mass of reactant should be equals to that mass of product. So in this process there is no loss of energy. Okay, and this is known as elastic collision. Now we'll discuss the kinematics of nuclear reaction. That is very important. So of nuclear reaction. Okay, suppose you have target nuclei. Okay, suppose you have target nuclei, its mass is m0. Okay, it's a very heavy nuclei. Speed is v equals to 0. An incident particle, let us denote this particle is on. Its mass is m on. Speed is v on. Momentum is p on, and kinetic energy is u on. Okay, kinetic energy is u on. So what you can write? P on equals to root over 2 m on u on. Okay, this particle or this target particle is bombarded by this incident particle. Okay, so that line is not proper on it. So suppose you have this particle, this target nuclei is bombarded by incident particle. So after that, Proton nuclei. So after nuclear reaction, there is a emission of Proton nuclei. Okay, let us denote this the Proton nuclei naming as 2. Okay, its mass is m2. Okay, velocity is v2, momentum is p2, and kinetic energy is e2. So what you can write, p2 equals to root over 2m2 e2, and let us assume that angle is phi. And also there is an emission of another particle. Let us note this particle name as 3. Its mass is m3. Okay, speed is v3, momentum is linear momentum is p3, and its kinetic energy is e3. So obviously p3 will be how much? Root over 2 m3 e3. Okay, so let us assume this angle is theta. So this is the scenario before nuclear reaction, and this is the scenario after the reaction. So particle on is or the target particle having mass m0, speed v0, since it is, so it is raised. The incident particle on is incident on this target nuclei. After that, there is a production of daughter nuclei that is noted by 2. Its mass is m2, velocity is v2, linear momentum is p2, kinetic energy is e2. So obviously you can write p2 equals to root over 2 m2 e2. Okay, and there is emission of another particle at angle theta. That particle is 3, mass is m3, velocity is p3, linear momentum p3, kinetic energy e3. So p3 equals to root over twice m3 e3. Now what will be the q value of this reaction? So can we write q equals to how much? Kinetic energy of product, so it will be E3 plus E2, because that product is here 2 and 3. Okay, and E1 because this particle is at rest. Okay, so in most of the cases they will provide you in exam, they will provide you that E3 E1, but you have to calculate E2. So how will calculate E2? So there is in any nuclear reaction that linear momentum will be conserved. Okay, or component of linear momentum will be conserved. So let us denote, this is your x-axis and this is your y-axis. So before reaction, that linear momentum along x-axis is how much? Root over twice m1 e1, right? No, before reaction that momentum is along x-axis root over twice m1 e1. And after reaction, so since this is at angle phi, that two particles, so that component along this axis, x-axis will be how much? Cos phi component, right? Root over twice m2 e2 cos phi, right? And for third particle, that component along this axis will be how much? Simply that cos component. So from x component of linear momentum, what we can write? Root over twice m1 e1, that should be equals to how much? Root over twice m2 e2 cos theta, right? Then you have root over twice, sorry, cos phi. This should be cos phi, and this will be root over twice m3 e3 cos theta, right? So from here, what you can write? Root over twice m2 e2, okay, cos phi equals to how much? Root over twice m1 e1. Then you have root over twice m3 e3 cos theta. Okay, let us assume this is your equation number 1. And from y component, so before reaction there is no y component, and after reaction you will have, for third particle you will have component along positive y direction. That will be how much? Root over twice m3 e3 sin theta, right?
Sin theta.
Exactly. And for this particle, it will be along negative y-axis, and that will be root over twice m2 e2 sine phi, right? So what we can write, since they are in opposite direction, so from y component, okay, so every component of linear momentum is conserved before and after reaction. So from x component conservation, we got this equation. From y component, what we can write, 0 equals to root over twice m2 e2 sine phi minus root over twice m3 e3, then you have sine theta, okay, equals to equals to 0 already you have written. Now if you rearrange it, what you can write,
twice m2 into sine phi equilibrium.
So it will be root over twice m2 e2 sine phi equals to root over twice m3 e3 sin थीटा. ठीक है, समझ में आया इतना? किसी को कोई डाउट है? Is it clear?
Yes,
Okay. Now make square of 1 and 2 and add them. Square both equation and added, then what you will get? So you square it. Let us assume this is equation number 2. So you square this equation and this equation. So 1 square plus 2 square. What will give you on the left hand side? So it will give you, see, cos square phi plus sin square phi, and this factor is common. So if I take this factor common, it sin square phi plus cos square phi will give you 1. So simply you will get 2 twice m2 e2. Okay. What about on the right hand side? What you will get?
2 times m1 e1 plus 2 times
So
m3
you will get twice m1 e1 plus twice m3 e3, then minus how much you will get? 4 m1 m3 e1 e3 cos थीटा. चेक करो, यही मिलेगा जब स्क्वायर करोगे. देखो, हाँ, रूट ओवर ट्वाइस एम ऑन ईऑन, इसका स्क्वायर तो यही देगा आपका. इसका जब बी स्क्वायर करोगे तो यहाँ पे आप क्या मिलेगा? ट्वाइस एम थ्री ई थ्री कॉस स्क्वायर थीटा. यहाँ पे देखो, इस साइड को भी ऐड करना है आपको, तो इसमें क्या मिलेगा? ट्वाइस एम थ्री ई थ्री साइन स्क्वायर थीटा. तो बी स्क्वायर टर्म में क्या मिलेगा? ट्वाइस एम थ्री ई थ्री कॉमन मिलेगा, साइन स्क्वायर थीटा प्लस कॉस स्क्वायर थीटा, दैट विल बी ऑन. सो दिस विल गिव यू दिस फैक्टर. एंड ट्वाइस ए बी करोगे तो 2 इंटू ट्वाइस एम ऑन ई ऑन ट्वाइस एम थ्री ई थ्री, तो वहां से 2 का फैक्टर आ जाएगा, बाकी स्क्वायर रूट के अंदर रह जाएगा. एंड ऑब्वियसली यू विल गेट दैट कॉस थीटा फैक्टर आल्सो. इज इट क्लियर? इज इट क्लियर?
yes.
ठीक है. अब यहाँ से E2 कितना मिल जाएगा? बिकॉज E2 वाज अननोन, दे विल नॉट प्रोवाइड यू E2, दे विल प्रोवाइड यू E1 एंड E3. सो व्हाट विल बी दैट E2? सो E2 विल बी सिंपली E1 M1 by M2, then you have E3 M3 by M2, then you have twice 2 by M2, right? 2 by M2 root of her M1 M3 E1 E3 into cos theta. Okay. Now what will be the expression for Q? So you got E2 in terms of E1, right? Now you can easily write that Q value. So earlier if I have defined that Q, that was E2 plus E3 minus E1. Okay, so Q was E3 plus E2 minus E1. Now I will substitute that E2. If I substitute that E2, then what will happen? it's E3 and E3, that will be common. So what you will get? E3 1 plus M3 by M2. Then there will be common of E1. So here you have E1, here you have E1. So that will give you what? That will give you E1 M1 by M2 minus 1. Okay, and last term is minus,
Sir, even.
this one will be E1 minus twice 2 by M2 M1 M3 E1 E3 cos theta. So this is the expression for Q. Okay, E3 1 plus M3 by M2, then plus E1 M1 by M2 minus 1, then minus twice M2 root over M1 M3 E1 E3 cos theta. Okay,
सर E1 M1 by M3 आएगा ना?
यहाँ पे
हाँ,
नहीं, देखो M1 है, इसको ट्वाइस M2 से डिवाइड कर रहे हो, है ना, तो M2 आएगा ना, M1 by M2.
okay,
ये वाला बोल रहे हो ना आप, ये वाला.
हाँ हाँ हाँ,
तो यहाँ पे देखिए आप, अगर बोथ साइड M2 से डिवाइड करोगे तो ये M1 by M2 हो जाएगा, ये ऑन हो जाएगा, और ये ऑन है आपका, तो ये कॉमन आ जाएगा, ये ठीक है.
ओके सर.
हाँ, ये वाला इसमें आ जाएगा आपका M3 by M2. ठीक है ये.
Yes, sir.
Shall I erase?
Yes, sir.
एग्जाम का डेट आया आप लोगों का?
अभी नहीं आया सर, वही 17 से 19 के बीच है सर.
अच्छा अच्छा, हो जाएगा आप लोगों का. ठीक है, आप स्टार्ट करेंगे. न्यूक्लियर फिशन. Okay, so nuclear fission basically happens in nuclear fission. Heavy nuclei, can you please mute your mic? Heavy nuclei will break into two nuclei. Two nuclei, they have almost same mass, not exactly same mass, almost equal, you can write. So if you remember that binding energy curve we have discussed, so for, I'm not writing exact binding plotting, not exact binding energy plot, but if you see, if mass number is increased, or for heavy nuclei that binding energy is less, right? So in that regime there will be nuclear fission. So nuclear fission, what will happen? Heavy nuclei will break into two nuclei. They have not exactly same mass, but you can say almost equal mass, and there is a release of large amount of energy. That energy release of the order of 200 mega electron volt. So in nuclear fission, a heavy nuclei will break into two nuclei, okay, and with emission of large amount of energy, that is around 200 mega electron volt. So basic mechanism I'm writing. So suppose you have uranium 92 to 35. So first what will happen? First what will happen? It will capture a neutron. Then it will go to excited state. Okay. So this is the basic mechanism. Any heavy nuclei will capture neutron. Then it will go to excited state. So that excited state is noted like uranium 92 to 36. Okay. So this is known as also known as compound nuclei or compound state. So now that uranium reached to excited state. So from excited state it will come to ground state, okay, by nuclear fission process. So in that process there will be, suppose you have two daughter nuclei, let us assume X Z on A on, or let us give simple notation X plus Y, okay, plus Kn. There will be emission of neutron also. K is some number. Okay, K is some number. So there will be two daughter nuclei with emission of neutron also, and there will be large amount of energy. Okay. So in this process, first heavy nuclei will go to that excited state by the emission or by the capturing of neutron. So after that, from that excited state to ground state, it will come by nuclear fission process. So there will be emission of or there is a production of two daughter nuclei, X and Y. Also there is a production of neutron, and there is a emission of large amount of energy. So I'll give two example, then I'll go to that mechanism, how it is happening actually. Okay, then I'll go to that condition when it will happen.
सर क्या
Sir,
k number of neutrons है ना?
Yes, I'll give example, then it will be clear. This is a basic mechanism. So x plus y, they can have large large number of combination. It's not fixed. X and y can have large combination, many combination you can say. But the atomic mass number of X is around in the vicinity of 95, or atomic mass of Y is around 140. ठीक है?
सर
Yes.
ये एनर्जी रिलीज होता है, ये पूरा बाइंडिंग एनर्जी का डिफरेंस से होता है।
हाँ, बाइंडिंग एनर्जी का डिफरेंस।
और सर दोनों का जो एक्स एंड वाई प्रोडक्ट होता है,
हाँ
तो एक्स एंड वाई दोनों का ही तो बाइंडिंग एनर्जी ज्यादा है
हाँ
यूरेनियम के जैसा।
हाँ,
तो
ज़्यादा है।
उस दोनों का डिफरेंस से ही ये 200 में भी रिलीज हो रहा है।
हाँ, वैसे वैसे ही करते हैं। जैसे यहाँ पे मैं आपको एग्जांपल देता हूँ, इसमें एनर्जी रिलीज कैसे करते हैं। जैसे आपका सपोज मान लीजिए आपका एक्स एंड वाई आ गया ना, एक्स एंड वाई का बाइंडिंग एनर्जी पर न्यूक्लियन अराउंड 8.5 MeV, ठीक है। और आपका जो यूरेनियम 236, इसका बाइंडिंग एनर्जी पर न्यूक्लियन है 7 MeV, अराउंड 7.6, ठीक है। तो इसका एनर्जी रिलीज कैसे कैलकुलेट करोगे आप? पर न्यूक्लियन इतना है, टोटल नंबर ऑफ न्यूक्लियन कितना है आपके पास? 236, राइट। इसको आप ऐड करोगे एक्स वन वाई का, तो टोटल मास नंबर कितना हो जाएगा? 236 ही होगा। और आपका बिफोर रिएक्शन कितना है? 236। तो यूरेनियम का 7.6 MeV है, तो टोटल कितना हो जाएगा? 236 इंटू 7.6, ठीक है। और प्रोडक्ट का क्या हो जाएगा? प्रोडक्ट का मास नंबर कितना है? इसका भी मास नंबर इतना ही होगा, समेशन करोगे तो। और इसका बाइंडिंग एनर्जी अराउंड 8.5 है, तो टोटल एनर्जी रिलीज कितना हो जाएगा? 236 इंटू 8.5 माइनस 7.6, ठीक है। इज इट क्लियर नाउ?
सर लार्ज कॉम्बिनेशन मतलब
अभी एग्जांपल देता हूँ, मतलब ये फिक्स नहीं है, अभी एग्जांपल दूंगा। मतलब एक्स न्यूक्लियाई वाई न्यूक्लियाई कुछ हो सकते हैं, बट मास नंबर अराउंड दिस होगा। अभी 2-3 एग्जांपल दूंगा, फिर आपको क्लियर हो जाएगा। ये फिक्स नहीं है, यही है आपका, कुछ भी न्यूक्लियाई हो सकता है ना, जिसका मास अराउंड इस रीजन में लाई करेगा, ठीक है। क्लियर है नहीं?
यस
ओके।
हाँ।
kn क्या है?
k नंबर है और n है न्यूट्रॉन, मतलब देयर विल बी इमिशन ऑफ न्यूट्रॉन आल्सो. लेट मी गिव 2-3 एग्जांपल, देन इट विल बी क्लियर. ये बेसिक है ना, इसके ऊपर एग्जांपल अभी दूंगा. हाँ, सपोज यू हैव uranium 92 235, then you have neutron uranium 92 236, then it will go to a krypton 3689 plus barium 56, then it will have how much, 144, and there will be emission of 3 neutrons. Okay, you can write like this also. Okay, this is one example. Another example is 92 to 35
सर
0
बेरियम का एटॉमिक नंबर क्या लिखा है?
56 plus 36, this, so atomic number should be conserved, you know. So 56 plus 36 92.
What is
In-
KR?
Krypton.
Crypto.
So again it will be 92 to 36, it will go to strontium 38, then you have 94 plus xenon 54 and 144 140 plus 2 0. Now you can understand. So here that x is this, y is this, and k is this. Okay. Now, what is the mechanism? How it is happening actually in nuclear fission? To describe this, Bohr and Wheeler give that model, okay, or theory. So इतना आप लोगों ने लिख लिया?
Yes, sir.
Yes, sir.
Okay.
So K is number of neutrons then.
Yes. So what they are saying, suppose you have uranium 92 to 35. It is capturing on neutron. So initially after capturing, it will go to that excited state, but initially it will have spherical shape. Okay. Okay. So this is the initial shape. So uranium captured on neutron and it goes to excited state. So since it has excess amount of energy, so it will start oscillating, okay, or it will start vibrating. So therefore there will be the change or deform in the shape. So due to this excess amount of energy, it will deform into the shape or ellipsoid shape. Okay. Now after that, there will be creation of positive center around this site. So there will be creation of positive center this side and this side. So due to this, there will be Coulomb repulsion, and Coulomb repulsion will again change the shape to dumbbell. So initially it was spherical, then it becomes elliptical. Then due to Coulomb repulsion, it will become dumbbell shape, or this is also known as critical state. Okay. So it's spherical, elliptical, dumbbell, and this is also known as critical state. So you see, again, there will be Coulomb repulsion, right?
सर दोनों पॉजिटिव ही
हाँ पॉजिटिव, ये आपका क्या है पॉजिटिव, मतलब है न्यूक्लियस की बात कर रहा हूँ ना, तो इधर क्या अभी आपका क्या रहेगा, प्रोटॉन रहेगा, इधर भी प्रोटॉन रहेगा, है ना. सो दैट्स व्हाई दे आर डिनोटिंग लाइक दिस. So initially, after capturing that neutron, it is in excited state. So they will start oscillating. So they will deform its shape from spherical to elliptical. So after that, they will create some positive center, and there will be repulsive force. That repulsive force again change its shape from elliptical to dumbbell kind of shape. Okay. Now you see there is again Coulomb repulsion. So Coulomb repulsion will try to separate this nuclei into two parts, but there is a surface tension. There is a surface tension. Surface tension will try to bring this nuclei into its original shape. But Coulomb energy will try to break this nuclei into two parts. Okay. Now, if Coulomb energy is large as compared to that surface tension or surface energy, then what will happen? It will separate into two nuclei. So if that Coulomb energy is large, then it will be separated into two nuclei. So this state is known as separated. But if the surface energy is large as compared to Coulomb energy, then it will come to this and this. So it will again regain its original shape. Okay. But if the Coulomb energy is large, then it will be separated. After separation, what will happen? Since both are positive charge, so they will repel. So they will accelerate in opposite direction. Okay. Now after that, when they are accelerated, they are far apart. Now what will happen? For heavy nuclei, that for stable heavy nuclei, that n by p ratio will be in what range? For stable heavy nuclei, that n by p ratio will be in what range? Anyone? So this should be in the range of 1.2 to 1.4. For low mass number up to 40, that ratio is 1. But for heavy nuclei, that ratio should, for stable heavy nuclei, that ratio should be in this range 1.2 to 1.4. But for this nuclei, that ratio is above 1.4. So what they will do? They will emit neutron particle. So after that, there will be emission of neutron particle from both nuclei. Okay. So this neutron is known as prompt neutron. Okay. This is known as prompt neutron. Okay. So after emission of neutron, they are in excited state. So what they will do? They will emit gamma photon. So after that, they will emit gamma photon. Okay. And this gamma is known as prompt gamma. Okay, so initially it is in spherical, then due to excess energy it will become elliptical. Due to Coulomb repulsion it will take dumbbell shape. After that, if that Coulomb repulsion is greater than that surface energy, it will be separated into two nuclei. If that surface energy is large, it will come to the original shape. If they are separated, they will be accelerated due to Coulomb repulsion. After that, n by p ratio of these both daughter will be higher than 1.4. Then what they will do, they will emit neutron to achieve this n by p ratio in the range of 1.2 to 1.4. And that emitted neutron is known as prompt neutron. After emission of neutron, they are still in excited state. So they will come to ground state by the emission of gamma photon. And this gamma ray is known as prompt gamma ray. Is it clear?
Yes, sir.
Is it clear to all? Now, what is the condition for spontaneous fission? So they derive that relation with the help of liquid drop model. So Bohr and Wheeler derive that condition for spontaneous fission process with the help of liquid drop model. ओके तो इतना समझ में आया सबको? इतना समझ में आया?
Yes, sir.
सर यहाँ पर कूलम्बिक एनर्जी ज्यादा है इसलिए न्यूक्लियर फोर्स का कोई रोल नहीं.
हाँ, कूलम्बिक फोर्स ज्यादा है यहाँ पे. ठीक है, चला इरेज नाउ.
यस.
हाँ, so what they assumed, when that shape deformed, so its volume will not be changed, right? So according to liquid drop model also, अगर shape को deform करोगे, its volume will not be changed, but binding energy will be changed. So what they have assumed, when you are deforming that shape, so volume will not be changed. But binding energy will change. Why binding energy will change? So volume will not change. When you are changing that shape from a sphere to elliptical, there will be no change in volume. Okay, because volume is depends upon mass number. Mass number is not getting changed. So there will not be change in volume, but of course there will be change in binding energy. Why? There will be change in binding energy.
टोटल बाइंडिंग
क्या change हो रहा है?
कूलम्ब एनर्जी ऑफ सरफेस टेंशन.
Exactly, good. So when you are changing that shape, so that Coulomb energy will be changed, right? Because it depends upon R, right? So there will be change in that Coulomb energy because it depends upon charge configuration also. And also surface area is getting changed, right? Surface area is getting changed. So there will be change in surface energy also. So that's why binding energy will be changed when you are deforming that shape. Okay. Now volume will be same. So what we can write? Uh, 4 by 3 pi r cube equals to 4 by 3 pi ab square. Okay, and AB can be written in terms of distortion parameters. So let us define epsilon is your distortion parameter. So A can be defined as R into 1 plus epsilon, and B can be written as R into 1 plus epsilon to the power minus half.
वो AB होल स्क्वायर है या सिर्फ B पे स्क्वायर?
हाँ, ए बी स्क्वायर है, बी स्क्वायर है यहाँ पे. एक्चुअली 4 बाई
वो प्लस वन है माइनस हाफ सर कैसे?
नहीं, ये आपका देखो बी है आपका.
अच्छा हाँ ठीक,
माइनस हाफ है.
समझ गया सर.
ठीक है.
ठीक है.
Now r cube equals to how much? AB square, right? Now due to this modification or that distortion, there will be change in surface energy, I'm not deriving this, but surface energy will be modified by a factor of. So when that there is a change
Sir,
in shape. Nah, yes.
प्लीज ये बताओगे मतलब ये a इज इक्वल टू b के वैल्यू कहाँ से लिए मतलब वो मिस हो गया मेरा.
कौन सा ये?
हाँ ये इज इक्वल
So
टू
yeah, that this is semi major axis, right? So semi major axis, this is just a mathematics. So semi major axis can be represented in terms of radius and distortion parameter. Epsilon is known as distortion parameter. So A can be written as R, where R is the radius of sphere into 1 plus epsilon. Epsilon is your distortion parameter. Similarly, B can be written as R into 1 plus epsilon to the power minus half. Okay, so
मतलब
definition in terms of.
इसेंट्रिसिटी है क्या?
नहीं, यहाँ पे इसेंट्री वो नहीं है आपका, जो सेंट्रल फोर्स में आप पढ़ते हो वो नहीं है, यहाँ पे डिस्टॉर्शन पैरामीटर बोलते हैं इसको. सो दैट ए एंड बी, ए सेमी मेजर एक्सिस कैन बी रिप्रेजेंट इन टर्म्स ऑफ डिस्टॉर्शन पैरामीटर and B also can be represented in terms of distortion parameter. Okay, so epsilon is here not eccentricity, distortion parameter. Now due to that change in that shape, there will be change in that surface energy. So there will be surface energy will be modified due to that change in shape from spherical to elliptical by a factor. So surface energy will be changed, or surface energy will be modified by a factor of 1 plus 2 by 5 epsilon square and so on. Also there will be change in Coulomb energy. So I am not deriving it. This very rigorous calculation. So due to this change in shape, there will be change in surface energy, and that factor is 1 plus 2 by 5 epsilon square and so on. And Coulomb energy will be changed by a factor of 1 minus 1 by 5 epsilon square and so on. So net change in energy. So this is the modified factor of surface energy, and this is the Coulomb energy modified factor due to change in shape. Now, what will be the change in energy?
Sir,
So
1 minus 1 by 5.
1 minus 1 by 5. So see, only surface energy and Coulomb energy will be changed. So you have learned that 5 terms in binding energy, a liquid drop model, right? Surface energy, Coulomb energy. Why that volume energy will not change? Because volume is not volume is constant here. Why that asymmetric term will not change here? Why asymmetric term will not change here?
सिमेट्री में कोई चेंज नहीं है.
हाँ, एसिमेट्रिक नहीं चेंज नहीं होगा इसलिए क्योंकि एसिमेट्रिक टर्म किसके ऊपर डिपेंड करता है? n माइनस जेड स्क्वायर, राइट? जब आप शेप को डिफॉर्म कर रहे हो n माइनस जेड तो फिक्स्ड है ना? n माइनस जेड तो फिक्स्ड है आपका, तो फिर एसिमेट्रिक जो एनर्जी उसका कोई चेंज नहीं होगा, बिकॉज एसिमेट्रिक एनर्जी बेसिकली डिपेंड्स ऑन दिस फैक्टर. सो ऑल आर फिक्स्ड व्हेन यू आर चेंजिंग दैट शेप. Also there will not be change in pairing energy, because anyway you are not changing that number of nucleon here. Okay, so there will be no change in volume energy, there will no change in asymmetric energy, there will be no change in pairing energy. So there will only be change in that surface energy of nucleus, and there will be change in Coulomb energy. So surface energy will be modified by this factor 1 plus 2 by 5 epsilon square and higher order term, and Coulomb energy will be modified by this factor. So what will be the change in energy? Delta E. Change in energy due to change in shape. So how will write? Binding energy of elliptical shape minus binding energy of spherical shape. So for sphere, epsilon will be how much? 0, right? Because if you substitute that epsilon 0, so A will be how much? R. B will be how much? R. Did you get? So it will become sphere. Okay. So what, the change in energy due to the change in shape is nothing but binding energy of elliptical shape minus binding energy of that spherical shape. So binding energy, all term will be same. So I'll not write all term, only I'll write that Coulomb energy and surface energy term. So for elliptical shape, that surface energy will be AS where S is your surface coefficient, surface energy coefficient, to the power 2 by 3, then you will have 1 plus 2 by 5 epsilon square, and I'm not writing higher order term. Then you have Coulomb energy term for elliptical shape, that will be AC Z square a की power minus 1 by 3, a की power minus 1 by 3, then you will have this factor 1 minus 1 by 5 epsilon square. Okay. Then for spherical, it will be simply, if you are subtracting it, and for surface energy you will have already minus term. So minus minus it will become plus. So as a की power 2 by 3. Okay. Then you will have Coulomb term. So it will be AC Z square a की power minus 1 by 3. So you see this term will be cancelled. This term will be cancelled. This term will be cancelled. Okay. So finally what you will get? Simply minus a s a की power 2 by 3, then you have factor 2 by 5 epsilon square, then you will have plus ac z square a की power minus 1 by 3 1 by 5 epsilon square. Okay. So this is your change in energy. So for spontaneous fission process, delta E should be equals to how much? So change in energy, this is a kind of, you see, change in energy, binding energy difference I'm taking. So this change in energy you can think like a Q value, because binding energy of product minus binding energy of reactant. So it's kind of Q value you can say. So for spontaneous process, what is the condition? That Q value should be positive, right? No?
Yes, sir.
So if so this factor should be greater than 0. So if you substitute it, so what you will get? AC Z square, then you will have a की power minus 1 by 3. Of course you have this factor 1 by 5 epsilon square, that should be greater than equals to as a की power 2 by 3. Okay, then you have 2 by 5 epsilon square. So epsilon square will be gone. Okay, 1 by 5 will be gone. Okay, so what you will get? This is a की power 2 by 3, this is a की power minus 1 by 3. So if you rearrange it in denominator, what you will get? Z square by a, because this will give you a की power 1 by 3. If you bring this in this side, you will get a की power 2 by 3. So 1 by 3 by 2 by 3 will be how much? 1. So that should be equals to twice as by AC. So as means surface energy coefficient, and AC equals to Coulomb energy coefficient. So if you substitute this coefficient term, you will get Z square by A, that should be greater than 51. Z square by A, that should be equals to 51. So this is the condition for spontaneous nuclear fission. So for any nuclei whose Z square atomic number square divided by mass number is greater than 51, they will only process that spontaneous fission process. Is it clear?
Yes,
So
sir.
just due to the change in shape, there will be change in surface energy and Coulomb energy. So you have to calculate that Q value by taking the difference between binding energy of elliptical shape minus binding energy of spherical shape. So that only two term will be different, all other term will be same. So only two term you have to take, surface energy and Coulomb energy, and you have to substitute it. And for Q value, that so for spontaneous process, Q should be greater than 0. If you take this condition, you will get Z square by A equals to greater than 51. So this is the condition for any spontaneous nuclear fission. Is it clear? Is it clear?
Yes, sir.
मतलब जिनका जिस भी एलिमेंट का Z स्क्वायर बाय A ग्रेटर देन 51 होगा वही फ्यूजन के अंदर जाता है।
हाँ, न्यूक्लियर फिजन के अंदर जाएगा। ठीक है, इज इट क्लियर?
सर इसमें वो जो एसिमेट्रिक एनर्जी सर क्यों नहीं कंसीडर किया?
हाँ देखो एसिमेट्रिक
n
एनर्जी में,
माइनस
हाँ जब आप शेप चेंज कर रहे हो, नंबर ऑफ न्यूट्रॉन नंबर ऑफ प्रोटॉन तो चेंज नहीं हो रहा है ना। जब आप शेप
हाँ सर,
सपोज
कॉम्बिनेशन तो सर अलग अलग हो सकते हैं एनजेड का।
देखिए, आप सपोज मान लीजिए आपके पास यूरेनियम 92 236 है, ठीक है, ये आपके पास है। आप जब शेप चेंज कर रहे हो, इसका एटॉमिक नंबर कितना है 92 है, नंबर ऑफ न्यूट्रॉन कितना है 236 माइनस 92। तो जब शेप आपका चेंज हो जाएगा, ठीक है
ओ
ना,
सर समझ
नंबर ऑफ
गया।
न्यूट्रॉन नंबर ऑफ प्रोटॉन तो सेम ही है ना,
हाँ
कोई
हाँ
चेंज
हाँ
नहीं होगा, ठीक है। ठीक है, अब लास्ट पार्ट इज न्यूक्लियर फ्यूजन। सो व्हाट इज न्यूक्लियर फ्यूजन, आप लोग बताओ
सर
थोड़ा।
न्यूक्लियर फिजन में से क्वेश्चन किस टाइप से पूछते
सॉरी योर वॉइस इज नॉट क्लियर, कैन
हैं?
यू
मतलब
प्लीज।
एग्जाम में जो क्वेश्चन आएंगे
हाँ,
उसमें क्या गिवन कंटेंट रहेगा?
एग्जाम में बेसिकली फ्यूजन, फ्यूजन से आपका क्यू वैल्यू का ही क्वेश्चन आता है, ठीक है। अभी तक तो इस तरह से कोई क्वेश्चन नहीं आया। क्वेश्चन कहाँ से आता है आपको मैं बताता हूँ। एक आपका सेल मॉडल है, लिक्विड ड्रॉप मॉडल है, बेसिक प्रॉपर्टीज है, ठीक है, और रेडियो एक्टिविटी है, यही मेन टॉपिक है, ठीक है। बट आपको पढ़ना सभी चीज़ है, क्योंकि आगे तो काम में आएगा ना सारी चीज़, ठीक है। अगर आएगा तो बहुत सिंपल क्वेश्चन आएगा आपका, जैसे क्यू वैल्यू कोई न्यूक्लियर फिजन दे दिया जाएगा, क्यू वैल्यू निकालने के लिए बोलेगा, इस तरह की क्वेश्चन आता है कि कितना एनर्जी रिलीज होगा इस प्रोसेस में, ठीक है। आपने देखा होगा, क्वेश्चन नहीं देखे आप?
सर ये देखिए,
हाँ, जो भी आएगा, जो डिस्कशन हो रहा है ना आपका क्लास में, उसी के अंदर ही आएगा सारी चीज़, जस्ट आपको रिवीजन करना है अच्छे से। एक होमवर्क असाइनमेंट मैं दे दूंगा आप लोगों को, क्योंकि आज लास्ट डिस्कशन है, फिर एक असाइनमेंट दे दूंगा, ठीक है, और आप लोग प्रैक्टिस कर लेना उसको, ठीक है। लास्ट टॉपिक जो है आपका वो न्यूक्लियर फ्यूजन है।
लास्ट डिस्कशन यानी आज न्यूक्लियर फिजिक्स खत्म।
हाँ, न्यूक्लियर फिजिक्स खत्म है, ठीक है। फिर मॉलिक्यूलर एटॉमिक स्टार्ट हो जाएगा आप लोगों का। जो भी डाउट होगा आप लोगों का हमेशा पूछते रहना, कभी भी पूछ सकते हो, ठीक है। So in nuclear fusion, what used to happen? Two light nuclei combine to form relatively heavy nuclei. Okay, and there is a emission of energy. Okay, so suppose you have X nuclei combine with Y and producing Z. So amount of energy release will be how much? Q equals to mx plus my minus mz. Okay, since there is a emission of energy, so that's why Q should be greater than 0. So what you can write, mx plus my greater than mz. So क्या हो रहा है, सेम थिंग, आफ्टर रिएक्शन क्या हो रहा है, आपका जो प्रोडक्ट का मास है कम हो रहा है, सो देयर इज अ डिक्रीज इन मास, सो व्हाट यू कैन से sum of the mass, so after reaction there is a decrease in the mass, so sum of the mass is losing and that mass is converting to that energy, right? So where that nuclear fusion used to happen, so again I am drawing this plot. If you remember the binding energy versus nuclear plot, so this was your plot, like, right? So this side, when that there is a light nuclei, they are very less binding energy. So what will they do? They will combine and they will try to go towards heavy nuclei. So That's why when they will go to heavy nuclei, there will be increment of binding energy. Okay, so lighter element basically combine to achieve more stability. Okay, so where that nuclear fusion used to observe, like sun, stars, right? Sun, stars, and also nuclear fusion reactor. Nuclear fusion reactor. So fusion used to observe sun, stars, and nuclear fusion reactor. Okay, so but three nuclear fusion reaction is the most potential that create huge amount of energy. So three nuclear reaction is very important. That is, one is deuterium reaction. Deuterium reaction. So what is actually happening? 1H2, this is your deuterium, combining with or combine with another deuterium, and it will produce 1H3 plus 1H1 plus 4.04 MeV. So that amount of release energy is 4.04 MeV. Then you have another reactions. So these are the reaction most important or potential nuclear fusion reaction. So another is deuterium tritium reaction. Deuterium tritium reaction. So on deuterium, 1H2, this is your deuterium. Tritium means 1H3. They will combine and they will form 2He4 plus a neutron and with emission of 17.6 MeV energy. Okay. Another reaction is tritium reaction. So 1H3 combine with one tritium combine with another, it will produce 2He4 plus 2 neutron and with emission of 11.3 mega electron volt energy. So these are the three nuclear fusion that is very important, and they are creating huge amount of energy. 4.404 for deuteron reaction, okay, or deuteron fusion. Deuteron tritium, when they are combined, they are producing 17.6 mega electron volt energy, and tritium that fusion, that will produce 11.3 mega electron volt energy.
वो
Okay.
2He4 के बाद क्या लिखा है?
कौन सा ये वाला?
हाँ सर
2He4 plus 2 neutron. 2 into 0 N1 means neutron.
उधर का दिख नहीं रहा.
अच्छा ठीक है, मैं इधर लिख देता हूँ.
सर सर वो ये ट्राइटियम वाली रिएक्शन
हाँ यस
सर उसमें प्रोडक्ट में आपने क्या क्या लिखा है व्हिच
हाँ
एंड
हाँ यहाँ पे लिख दिया मैंने ट्राइटियम
अच्छा ओके
ओके.
सर कितना एनर्जी कितना लिखा है? 113.
11.3.
ओके.
हो गया?
Yes, sir.
Okay. Okay. Now, solar fusion. That is your last topic. Okay. So in sun and star, in most of the cases, they contain lighter element like on hydrogen. Okay. Okay. And few stars
Yes.
basically contain lighter element as well as relatively heavy element. Okay. So based on their composition, there are two kind of nuclear reaction or nuclear fusion is happens. So the name basically they have given on is proton-proton cycle. In proton-proton cycle, this is most dominant nuclear fusion reaction in all stars and sun. Okay. So in proton-proton reaction, what used to happen? That lighter element like on hydrogen combine with hydrogen, and that lighter element combine to become heavier, and they try to achieve that stability. So suppose example on this is this has very less binding energy, right? So they will combine to become stable. So among lighter, which one is more stable? Like 2Ag4, right?
वन एच
2Ag4,
वन
हाँ 1H1
Yes, sir.
का बाइंडिंग एनर्जी बहुत कम है। अगर वो कंबाइन होकर 2Ag4 तक चला जाएगा तो लाइटर एलिमेंट में से 2Ag4 ज़्यादा स्टेबल है क्योंकि वो मैजिक नंबर कंटेंट करता है। ओके, सो that lighter element will try to combine and they try to achieve stability. So they will combine and they will form that helium 4. Okay, 2H4. So that basic cycle is, suppose you have on, it will combine with another that hydrogen, then what will give? It will give on H2 plus positron, and there is a neutrino. These things also in GATE they used to ask. So what they will give you that X particle, that what that X particle will be. So this is like a lepton number conservation, right? You please use that concept of lepton conservation law. Okay. So sometimes they used to ask
Yes, sir.
what that X particle will be. Okay. So now what will happen? So on the two on H1 will combine and they will produce this on H2. Now on H2 will combine with on H1. Then what it will give? 2H3, right? And there will be emission of photon. Okay.
Yes.
Now what will happen? 2H3. Okay, this is 2H3 will combine, and it will produce what? 2H4 plus 2 on H on, and there will be emission of energy. So this is first chain. So you see, you got 2H4. So in that way, they will combine and they will produce 2H4. So hydrogen, it was not stable, but due to that nuclear fusion, after nuclear fusion, they will produce 2H4, and there will be emission of energy also, like gamma you can clearly see. Now there is another chain. This is first chain of reaction. Another change can be possible, that 2H4 can be combined with 2H3, and what it can give? 2He3 combine with 2He4, and what it can give? Barium 4,7, right? 4,7, and there is emission of energy. Okay, barium,
Yes, sir.
there is emission of energy, and now what will happen? That barium 4,7 will combine with hydrogen, and what it will give? Boron, right? Boron 5,8,
Yes, sir.
right? And there is emission of energy. Now what will it will do? Boron, sorry, barium, there will be modification. 1 minute. Now this step will not happen. So barium you got na. Now barium 4,7, sorry, 4,7, it will absorb one electron, because inside that star it has very large amount of it has very large temperature, right? So there will be huge number of electron also, because that electron is basically creating due to that heavy temperature. So that star basically, or sun basically, treated as a plasma, so there is a huge amount of electron. So that barium will absorb this electron, and it will convert to what? So inside star or sun, you have many number of electron. So barium will absorb one electron, and it will become what? So this is like a -10, right? So it will be lithium 3, then 7, right? 3, 7, then there will be this particle, neutrino, right? Is it clear? Now lithium 3, 7 will combine with on hydrogen. Then what it will give? 2 helium. Okay, and there is a emission of photon. So this is known as second cycle or second chain. So here you will get, you see there's a production of helium. Okay.
Yes, sir.
Okay. Shall I erase?
Yes, sir.
Last is another chain is possible. That is, you have barium, right? 4, 7. It will combine with one hydrogen, and it will give what? Boron 5, 8. Okay. Then boron 5, 8 will be decays like barium 4, 8 plus positron plus neutrino. Okay. And barium 4, 8 will decays to what? 2H4, right? Or you can say He24, He24, and there is emission of photon. This is your third chain. थोड़ा सा बोरिंग है टॉपिक, इसीलिए यहाँ से क्वेश्चन भी पूछता नहीं है, ठीक है? बट बेसिक मैकेनिज्म आपको जानना जरूरी है कि आपका इनसाइड नेचर में क्या हो रहा है, इनसाइड स्टार, इनसाइड सन में क्या हो रहा है, ठीक है? थोड़ा सा बोरिंग है ये. Okay. Last your carbon cycle. So this is all about your proton cycle. So last is your carbon
ये बात
cycle.
बताइएगा.
हाँ.
सर
Yes.
सर ये जो रिएक्शन है ये इसी ऑर्डर में होते हैं, जैसे फर्स्ट चेन, सेकंड चेन, थर्ड चेन?
हाँ, दीज आर पॉसिबिलिटी। मतलब हर चेन में क्या हो रहा है, देखो अल्टीमेट क्या है कि हीलियम 24 ये जो है कैसे आ
Yes.
रहा है। तो डिफरेंट डिफरेंट ये है मैकेनिज्म है, और डिफरेंट डिफरेंट वे है कि जहाँ आप हीलियम 24 आपको मिलेगा। ठीक है, एग्जैक्टली यही हो रहा है आपका सन स्टार के अंदर। एंड सेम थिंग दे आर अप्लाइंग, जैसे मैंने 3 इंपॉर्टेंट रिएक्शन आपको लिखाया था ना पहले, वो सारे चीज़ आप एक्चुअली न्यूक्लियर रिएक्टर में यूज होता है। न्यूक्लियर रिएक्टर जहाँ बनते हैं ना, जैसे ड्यूट्रॉन ड्यूट्रॉन रिएक्शन, ड्यूट्रॉन ट्राइटियम रिएक्शन है ना। ड्यूट्रॉन ड्यूट्रॉन क्यों यूज करते हैं बेसिकली, क्योंकि आपका जो सी है वहाँ पे देयर इज ए लार्ज अमाउंट ऑफ ड्यूट्रॉन, राइट। सो इट्स वेरी रिच। ओके, इजीली अवेलेबल, सो यूज करते हैं ये सब। ठीक है, सारा एरियाज नाउ।
Yes, sir.
So last is your carbon cycle. सो प्रोटॉन प्रोटॉन साइकिल कहाँ पे बेसिकली डोमिनेंट है हर जगह के पे, क्योंकि हर स्टार एंड सन पे क्या होता है, लाइटर एलिमेंट होता है, बट कुछ स्टार्स पे क्या होता है, रिलेटिवली हैवी एलिमेंट होता है, तो वहाँ पे कार्बन साइकिल पॉसिबल है। तो एक साइकिल और है बी आपका कार्बन साइकिल। ठीक है, फॉर कार्बन साइकिल दिस शुड बी अवेलेबल लाइक कार्बन 612, then carbon 613, नाइट्रोजन 714, ये सारे आपको होना पड़ेगा स्टार्स के अंदर 715। ओके, so what it will happen, first carbon 612 will combine with on hydrogen and it will produce what, carbon, oh sorry, nitrogen 713, right, and there is emission of gamma. Now nitrogen 713, okay, will decay to carbon 613 with emission of positron and neutrino. Now carbon 613 will combine it on hydrogen, okay, and it will give you nitrogen 714 with gamma. Okay, then nitrogen 714 will combine with one hydrogen, it will give you oxygen 815 and there is emission of gamma. Now oxygen 815 will decay to nitrogen 715 plus positron emission plus neutrino. Okay, positron emission plus neutrino. Now this 715, nitrogen 715 will combine with on hydrogen and it will give what, carbon 612 plus helium 24. So this is all about your carbon cycle. Okay, so for carbon cycle this should be available. First carbon with combine make fuse with hydrogen, it will produce nitrogen. This nitrogen will decay to carbon 613. Carbon 613 will combine with on hydrogen, it will produce nitrogen 714. It will combine with on hydrogen, it will give you oxygen 815. Oxygen 815 will decay to nitrogen 715. Nitrogen 715 will combine with on H1, it will produce helium-2,4 and carbon-612. So this is all about your carbon cycle. Okay, so this is all about your nuclear physics syllabus. I hope you will get all question and you will do it properly. Okay. Yes.
Yes, sir.
Okay. So we should stop here. Now we'll discuss from next day. We'll discuss spectroscopy and atomic physics. Okay. So you solve all this question. I think you will able to solve all question. If you have any problem, if you are facing any problem from any question, you just give me that call, or you can chat me. Okay, I'll immediate reply you. Try to solve one question. I hope you will able to solve all questions. Okay.
Okay.
Yes, sir.
Okay. So we should stop here. Okay.
So
Thank you, sir.
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 Welcome. Okay. Happy weekend.
Thank you, sir.